Welcome to this second online video session with the principles of communication systems. So in the last video I have discussed about what we mean by amplitude modulation, and also we have gone through some mathematical analysis of the time and frequency domain description of the amplitude modulation. So, and also we discussed about briefly the general block diagram for the communication system. So the main point what we discussed in the last session was time and frequency domain description of amplitude modulation. So guys, in that case, time and frequency domain description, what we have discussed was we have started our discussion by considering one instantaneous message signal or a modulating signal having amplitude AM and frequency FM, that is AM cos 2 pi FMT, as you are observing here. Similarly, we considered high frequency carrier signal C of t, and directly we got the modulated signal S of t, and we gone for the Fourier transform. Okay, so the main difference between time and frequency domain description of the previous AM and this single tone AM is that here now we'll consider only one amplitude as usual, and also we'll consider the carrier signal having single amplitude AC, and directly we are getting equation for the modulated amplitude modulated signal, that is AM signal here. Okay, no doubt. Now what we are doing, instead of going for the direct Fourier transform of this one, so here what we are doing, we are going to substitute for m of t in equation number 3. We are going to substitute m of t equal to am cos 2 phi fmt here in equation number 3. So k dot m of t you replace by am cos 2 phi fmt, and outside cos 2 phi fct will be remaining as it is. Okay, so here k dot am will be replaced by one symbol that is known as modulation index. Okay, or mu. Notations will vary from one textbook to another one. So m or mu are invariably used to represent modulation index, that is equal to amplitude sensitivity Ka multiplied by the amplitude of the actual amplitude of the modulating signal. Okay, so this much you should remember. This is also acting like a formula. Now our equation of AM signal will be like this: AC plus mu or m AC cos of FMT goes to cos of 2 phi FCT. Okay. Now what we can do, we can multiply each term in this bracket by cos 2 phi FCT. Okay. AC if you multiply it by cos 2 phi FCT, what we are getting, AC into cos 2 phi FCT, plus again you multiply these two, what we have, mu AC, okay, cos 2 phi FCT into cos 2 phi FMT. Now we know that there are two cosine terms are there. We can apply the compound formula of trigonometry here, that is cos A cos B, because here FC is there, FM is there, both are different. FC is greater than FM, so both are different here. So A and B here also both are different. We can apply this compound formula. So the formula what we can get, it will replace product of two cosine terms by the sum of two cosine terms here. Okay, so what we can get, half into bracket cos of A plus B plus cos of A minus B. So in the same way, if you replace, apply this one, and what we will get here, AC cos 2 phi FCT plus half you are getting here mu AC by 2 cos 2 phi FC minus FM, and here FC plus FM. So this will be the lower and upper side ones we are getting. So once you apply Fourier transform, so here somebody has asked me how we are getting these things. Okay, so Fourier transform formulas are there. So when you apply the Fourier transform to the cosine here, so here you can see, so Fourier transform of cos 2 phi FCT, a standard formula is there. We will get dou of F minus Fc plus dou of F plus F. In terms of impulses we are getting. Okay, because cosine normally represented in terms of exponentials. If you apply Fourier transform to that one, what we are getting? We are getting its equivalent frequency domain representation in terms of impulses, dou of f minus fc plus dou of f plus fc, containing single impulse centered around at the lower and upper side bands, plus again we are getting mu ac by 4. Okay, so this another divided by 2 we are getting here it was by 2, now we are getting by 4. Here also you can see AC is there, now it is divided by 2. So when you apply Fourier transform, we are getting f minus ft plus f plus fc divided by 2. Here also it will be divided by 2. That extra divided by 2 is multiplied with this 2. That's why we are getting mu AC by 4. Hope you are understanding this. Okay. Like that we are getting this equation number 6. That is a Fourier transformation of this equation. Hope you now you are understanding. If not, you can go through your previous that is a Fourier transform formulas. There you can get Fourier transform of cosine is this, and its frequency separate version automatically you can make out like this one. Okay, I think the point is clear. Thank you. Next one. After this we included that small derivation, that is a modulation index in terms of maximum and minimum amplitudes. In the exam, if they will ask you just obtain an expression for the time and frequency domain description of AM, then it is not required here, up to 8 marks. Okay, specifically, or if it has been asked for more than 8 marks, then you can include this. Remember, specifically if singleton AM is asked, or if it has been asked for more than 8 marks, then you can include this one. Okay, he is going to ask it separately because it is a separate derivation kind of thing he is looking here. Okay, so next we can go for the power relations between our lower side bands and upper side bands and carrier. Okay, so power relations in AM it will indicate the total power, hence it will become equal to the total carrier power plus lower side band power plus upper side band power. Okay, so here we are going to include the RMS value with R as a resistance. Okay, so carrier voltage square by R if we do, V equal to, that is a amplitude AC by root 2 will take, because we are considering only RMS value here. Okay, so you need to multiply it by root 2, convert it into peak value. So AC by root 2 whole square, because it is VC square divided by R, you will get AC square by 2R. So here amplitude is AC. If you take its RMS value, if you want to take, you need to divide it by root 2. Similarly, here also you will get mu or m. I told here mu was there in our previous derivations. Now here there is m. It could be mu or m. Here the amplitude of the side band is going to be m AC by 2. Okay. Again m AC by 2 is divided by root 2 because we are using RMS values. Okay. That is square divided by R if you do. If you simplify it, you will get this much, m square by 4 into PC. Similarly, upper side band, same thing. Mu AC by 2 is there, means m AC by 2. Again, you need to divide it by root 2 because to get the its R equivalent RMS value. Again square, again you get m square by 4 into PC. Means what we are getting, the carrier power is half, and sideband powers are again once again reduced by half respectively. Okay, that's what I'm telling. M and mu are invariably used to indicate modulation index. So these are the quantitatively we are getting some kind of equations in terms of their respective amplitudes and modulation indices for the carrier power and sidebands. Okay, so later if you want, now you can take the ratio of total to carrier power or sideband power to carrier power, everything you can calculate like this. So here you can see the total average power is given by PC plus LSB plus USB. PC plus LSB is m square by 4 PC. In terms of PC is keeping all the powers. Okay, PT equal to PC into bracket. If you take PC as a common, what you will get inside, and if you simplify it, you will get the relationship between the total power and the carrier power as PT equal to PC times 1 plus modulation index square by 2. Okay. Similarly, we can get the ratio between the total sideband power and total power. Okay. Total sideband power, if you add these two, okay, these are the two sideband powers. What will get? M square by 2 PC. We can simply add these two, m square by 4 plus m square by 4. What will get? 2m square by 4. Means m square by 2. 2 numerator and denominator 4. 2 ones are 2 2 0. Denominator will get 2. Total power is going to be how much? Total power, here you can see, just now we got PC into bracket 1 plus m square by 2. So PC got cancelled. What we left here is the relation between the total power and sideband power only in terms of m square. And we know the range of values, minimum and maximum values for the modulation index. Maximum value for modulation index is 1. Means for this maximum value of m, we will get maximum efficiency. So this will indicate sideband power to the total power. This ratio is called as efficiency of m. So if we substitute for m here, m equal to 1, 1 square, that is 1, divided by 2 plus 1, m means 1 square. What will get? 1 by 2 plus 1, 1 by 3. That is 33.33% will get. That will give the efficiency of EM system. How will get it? It is the ratio of total sideband power to the total power, like that. Okay. So many times it has been asked, guys, so better practice these derivations single tone clearly. Okay. So next you can see. So this is a frequency domain representation. Just now I told how we, after applying the Fourier transform, we are getting here. This arrow market is indicating both S of t and S of f have the frequency Fourier transform domain pairs. Okay. So if you add the power like this, you will get all the power relationships as we discussed in the previous slide. So hope guys you understood, because I found it once again to discuss it clearly, because it is very important, because already I have discussed that one in the last video. So this derivation with the time and frequency domain description of AM for single tone AM is very important as far as the power relations is also concerned. Okay. Apart from that, you also have to be focused on small derivations. Okay, like modulation index in terms of maximum and minimum amplitude, that one, and these power relation derivations. Even at the end of time and frequency domain description AM before single tone, we have did some small derivations. Those also you can go through it. So hope somebody has asked how to get Fourier transform. That point is now clear, I think. So these are some of the VT question papers recently I have taken from 17 scheme here. For your scheme, it will be different. Of course, 60/40 scheme only, but some things are removed and some things are added for your batch. So here, normally I am referring 17 scheme question paper, because 15 scheme question papers and syllabus and your scheme are totally, to some extent, to more extent, they are different. Of course, but the question wise, if you want to know how the particular questions will be asked, obviously we can refer to that. So right now for the example, for you to explain, I took two question paper snapshots here. This one is has been asked in the June July, and this one is December January. Okay, this one is June July question paper. You can see here, illustrate the time domain and frequency domain characteristics of standard AM produced by a single tone. Just now I have discussed. 8 marks it has been asked. So not necessary to do the modulation index in terms of maximum and minimum amplitudes. That will be asked separately. If it has been asked for different marks, you can do it. Right now it is not required. You draw the diagram. Waveforms you must have to draw. It is very much important. Waveforms in the beginning I have told, and then do the derivations starting with m of t, c of t. You are getting s of t. In s of t again you resubstitute m of t and manipulate that equation, expand that equation, then you apply the ft, and already explained how to use the ft pairs to get its equivalent frequency domain representation. So here only he has not asked anything about power relations. Unless and until it has not been asked, don't go for that. Don't go for doing power relations. Okay. So another B section for 8 marks. Here you can see a carrier wave C of t equal to 4 sine 25 FCT has been asked. Okay. So here the FC is going to be 500 kilohertz and AC is 4 volts. This is how you have to make out. AC is 4 volts, FC is 500 kilohertz. Is amplitude modulated by an audio wave 0.2. 0.2 it will indicate it is a modulating signal. Okay. 0.2. So 0.2 it will become AM. Okay, sine of 3 into bracket. So this one here I think we need to simplify this equation so that we can get single sine function out of this by applying the trigonometric ratios here, because this will contain sine of something here. So you have to apply some trigonometric relations, then we will come to know how to add an AM you will get, but FM we need to find out here. So but FM I think we can get here. You can see if here this term and this term they will contain same, means 500 hertz. Okay, it is omega is there, sorry, FM is there. So whenever you get two frequencies, sine containing two frequencies, you need to apply arithmetic mean or some mean you will apply to get the one single modulating frequency. So this is how guys you have to make out from the given problem the data AM, AC, FC and AM and FM. So what is asking? Determine the upper and lower sideband and sketch the complete spectrum of the modulated wave. So how will determine the upper and lower sideband here? The derivations whatever you did, we need to remember them because they are now acting like formulas here. Estimate the total power in the sideband, that is PC into bracket 1, you refer to that equation. Okay, so that equation you have to use here. So try this one. If you won't get, you quote me in the WhatsApp group, I will try to resolve it. So next one, this one is normally has been asked in December or January 2019-20 question paper, again 17 scheme. Describe time domain analysis of AM with a neat relevant spectrum. So both time and frequency domain related waveforms neatly you have to practice guys here, because they will carry out of 8 maybe 3 to 4 marks, 3 marks around. Okay. So next, with a neat diagram, explain the circuit of switching modulator with relevant signals. So this we are going to discuss today. Next one. So these two question papers I wanted to show you to just make you aware that what kind of things you will be asked so far. Now you can see we are able to answer here the first A bit and the first A bit here also 8 marks. So after this we will go for discussing switching modulator, so that we are also able to answer for this 7 marks. So next one, the switching modulator circuit diagram is there here. So switching modulator is nothing but which has been asked. You can see here one question I will be showing here has been asked in the OT question paper 16-17. Okay. Wait a minute. Okay. So it is a diode circuit used to generate AM signal. Okay, so here you are applying modulating signal, okay, in series with the C of the carrier signal. Understand? So plus minus, they are connected in series, so that V1 of t, that is nothing but sum of these two, M of t plus C of t, applied as input to the anode of ideal diode. Remember guys, we are using ideal diode here, which is acting like a switch here. Okay, we switching between either V1 or, sorry, I have to write okay, V1 and V2, sorry, V1. So maximum amplitude is going to be is that of the V1. So how its on-off condition is controlled here. On-off condition of this diode is controlled by both these two, C of t and M of t. Whenever C of t is greater than M of t, you can see here greater than 0 means greater than M of t. C of t is greater than M of t means anode, whatever voltage you are applying is more than the cathode voltage. Cathode voltage means modulating voltage. Whenever cathode voltage means C of t is greater than the cathode voltage, that is M of t, you will get it is on. Okay, that is V1 of t is allowed. Otherwise, it is reverse biased, no output voltage. Okay, so the condition here is that amplitude of the m of t should be, that is a modulating amplitude should be very much less than that of the carrier amplitude. That one thing we have to make sure. Okay, so this is all about V1 of t and about some bit about circuit I have explained here. So next one we can see, this one will show the graph relationship, graphical relationship between V1 of t and V2 of t. V1 of t is means what? Voltage across the diode. Okay, so V1 of t is nothing but input voltage applying to the diode. V2 is the output voltage we are getting. Okay, V1 of t versus V2 of t, they should be linear. Now you can see, as I already told, your diode is switching back and forth, means it is going to generate your train of pulses. Okay, so what is happening here is that, you try to understand here, your input V1 of t is now multiplied with these on off on off on off. This your V1 of t should be now multiplied with this train of pulses. Okay, so let me cover this fast so that I will once again, because of the battery power. So this is your periodic pulse train here. Now V2 of t is going to be V1 of t multiplied with Gp of t. Okay, what is V1 of t? V1 of t will, you already know, m of t plus carrier signal AC cost of LCT, that is multiplied with the train of pulses here. Okay, Gp of t, now we can represent it by half plus 2 by pi cost of some series we are using here now to represent this periodic signal. Okay, this periodic signal is represented by this series that we are using here. Further harmonics we are not considering because of the very small amplitude. Okay, so that's why we are considering only first two terms here. Okay, you need to remember this, not to worry. So this, for the series sequence we are using this equation, and in that only we are considering the first two terms, because further terms their amplitude will be go on decreasing. Okay, so next what will happen, if you multiply these two, okay, simply you multiply these two, and rough sketch I have shown here. For some of the may be getting the doubt here, refer to the video, see it again one or two times, you'll understand easily how to get V2 of the expression. Okay, so after this one, if you look at this circuit diagram, V2 of t is nothing but output of the diode. Then we will be having band pass filter that is tuned to FC. Okay, this will absorb only FC component.